Okay, Calc BC Unit 2, Assignment 13, Pretest. So here's all the answers if you need to check them. You could pause the video. I'm going to scoot it up a little bit in a second, so just pause it, check all the ones you can see. And there's all the rest. Check them. Pause it if you like. Okay. So on your test, you will have some limits that you will determine from a graph given to you. You should probably assume that the dots line up with nice values, unless I otherwise tell you, vertically and horizontally. I mean, this one does look like it's 1.5, so I'd probably clarify that for you. This one appears to be -1, so, okay. What's the value of the function at -8? It is where the dot is. It is 7. What's the limit as you approach -8? Well, both sides agree, which they need to, and they both approach 5. So the left side and right side have to agree. C, as approaching -6 from the right side. So here's -6 approaching from the right side. It's going to -infinity. And I want you to write that, even though technically it does not exist as the answer. What happens as we get to infinity? Right, that's the right end behavior, and it looks like it's going to its horizontal asymptote 1. As you approach -3 from both sides, it's going to positive infinity on both sides, but I would say that this is an answer that we should not write that. We should say does not exist, non-existent, no limit. So for two-sided limit, I don't want you to put infinity, okay? Letter F is a derivative. As you push -6 from the right, it's actually positive infinity. It's a positive slope. People are going to accidentally put -infinity as if the question was the same as part C. It is not. It's a derivative. Slope is positive. Left, right, it's going up. G, list all the values of x for which f of x is not continuous. That would be any holes, jumps, -8, vertical asymptotes, -6 open dot, -3, -1 is okay. List all the values for which f of x is not differentiable. Well, if it's not continuous, it's automatically not differentiable. So any of the answers from the previous problem, plus any corners or cusps or sharp changes to graph. So -1 would be the extra answer on that one. Okay, so this should be quick and easy. We're going to possibly do a sketch of a derivative graph, which I don't think I put on any of the assignments yet, but that's something we did last year. And so essentially what we want to do is look for, I'd look for obvious slopes, like 0 slopes. And we'll assume that's 0. Now I'll tell you on test A if they're 0 or not. So on the ends, we're always going to put like an open dot because derivatives are two-sided issues. So if you're on the edge, you only have one side, so derivative technically does not exist there. These are going to be open dots if the derivative changes. If it's smooth, like at 5, then it's a solid dot. So that's the difference. That makes a difference. That's an important difference I need to see. Maybe look for any constant slopes. That looks like a straight line up 1/1. So that's a constant slope from 2 to 3 of 1. Open dot to open dot because at 2 and 3, the slope doesn't exist because you have a sharp corner. We might say look for vertical tangents. So at 4, vertical tangent means slope blows up, which means you're going to have a vertical asymptote here, and also at 6. Okay. And then, kind of just maybe there's a vertical tangent here on the left side. I would tell you for sure not. Well, let's go ahead and go with that this time. So if you get these basic things nailed down, it's going to make the graph a lot easier. So here we're starting at 0, and it's going negative, negative, negative to negative infinity. So something like this could be one way of interpreting it, depending on how I set it up. Based off what I've been saying, that's what we do. That's already there. From 3, it's going from 0 and it's going to positive infinity. The graph is going to positive infinity. The slope is going to positive infinity. It's the slope. On the right side, you might be tempted to do the same thing, but that's actually a negative slope. So it's going to negative infinity and then getting closer and closer to 0. And then it's going more negative, going to negative infinity again. I need arrows on the ends. I need solid or open dots at important places. So vertical asymptote lines. Okay, number 3, locate the removable discontinuity. A removable discontinuity is a hole in the graph. So essentially I'm telling you to find the hole. Now you could say, well, x equals 6, and then here the thing that makes this 0 is 6 and also negative 6, right? So when you get the same one on the top and bottom, that probably means that there's a hole in the graph. And this would be vertical asymptote. So I guess we could just say the removable discontinuities at 6. Now another way we could do it to just sort of help someone understand our answer is we could draw a graph. Now at negative 6, positive 6. When x equals negative 6, I think we're going to vertical asymptote for sure. It's blowing up. And as we go to negative infinity, these are the dominant terms. And so it's a negative over a negative. So it's actually going to positive 1. Horizontal asymptote on the left. On the right, we're going to positive infinity over negative infinity. We're going to negative 1. And in fact, to the right of 0, it's the same thing as x minus 6 over negative x minus 6, which is negative 1. So it's actually this flat line here to the right forever. And then here it goes like that. Up here it goes like this. And there is a hole at 6. Anyways, I guess I would be fine with you just saying that it's at x equals 6. But if you said negative 6, now I'd be looking for at least something here to make me feel like you knew what you were talking about. Okay, so removable discontinuities are just holes. Point discontinuities are another name for it. So you're going to potentially have problems like all those. Now this next chunk of problems, so pretty much 4 to 19 or so, these are going to be limits that we're going to solve algebraically without graphs. And just to let you know, on the actual test, it won't be this many. There will be 8. So just keep that in mind. Variety of techniques here, no L'Hopital's rule, okay? If you want to double check an answer, sure, but I got to see the regular. Now substitution, 3 times 2 minus 5. 6 minus 5 is 1. Okay, that's pretty easy. This one's 8, super easy. This one is natural log of e squared. That's not good enough for your final answer. You should say 2 for the final answer because you either moved it in front, power rule, or you say whatever is e2 to get e squared, 2. Natural log e is 1. Number 7, we're going to infinity, so we're looking for dominant terms. They have the same degrees, the ratio of their coefficients. So we'll say negative 2/3. You usually don't leave the negative in the denominator fraction, put it in front or on top. Now, I would be expecting at the very least that you circled the dominant terms that you pointed out to me. Okay, that's super easy. Same thing here, dominant terms. This one's bigger, so and it's positive or negative. So I mean, it's going to positive infinity over negative infinity, so it's going to be a negative answer. And here you could have said it's going to positive infinity over negative infinity, so it's going to be a negative answer. We're not going to do L'Hopital's rule, though. We're looking at dominant terms. This one's getting way bigger than that one, so it's going to 0. Number 9, going to negative infinity. Don't miss the negative. These are dominant terms. You got to put absolute values around this. If I don't see that in your work, then I might take out points. Probably will take out points. So you got to be careful. We're going to negative infinity. So you might be like, oh, well, if it's 2x or 3x, it's negative infinity over negative infinity. Actually, but the top one gets squared and then to square root. That's going to be a positive infinity over negative infinity. We should get a negative answer. Okay. This is always good to write down. Now, so the top's going to end up being positive and the bottom is going to end up being negative. So it's going to be negative 2/3. Okay. Gotta watch out for the square root, the squaring of a negative, losing that negative. Even when you take square root, it's going to be positive. Here we're going towards 2, so it's going to be 8 minus 2 is 6 minus 6 is 0 over 0. We're not going to do L'Hopital's rule, so we're looking for a hole in the graph. Now, we don't need to do rational root theorem. You could if you want, but quickest way is to say, oh, well, I know it's got to be a 2. I know I got to be able to get x minus 2 out of the top because that's where that 0 is. If this is causing 0, and there's one of them in the top causing 0 too. I just need to know what the rest of it is. So synthetic division, we're skipping rational root theorem. We're going to do synthetic division. Any missing terms put a 0. Drop that. Add. Should get a 0 at the end. If you don't, something's wrong. Now, these are the coefficients of your new x squared plus 2x plus 3, which we don't really need to have that factored, which I don't think we factor. Its roots are irrational. But here's the whole. So we can cancel it out. Plug 2 in here. It's going to be 4 plus 4 is 8 plus 3 is 11. Okay? That would be the work to show. Negative infinity, dominant terms. It's going to be a 2x, absolute value. It's going to be a positive infinity over a positive infinity. So we should get a positive answer. So the top, it's absolute value of 2x, which is going to force it to be positive 2. Bottom has a negative, but you're plugging negative in it, so that's going to be positive, right? So the answer is going to be positive 2. Okay. Number 12. If you plug a in, you get a cubed minus a cubed, which is 0. A minus a is 0. So it must be a whole. Trying to factor this out. This is the difference of cubes. So it's going to be x squared, ax in the middle. Same, opposite, always positive. That's the hole in the graph. Maybe write a note that it's a hole. Plug a back into here, and we get a squared plus a squared plus a squared, which is 3a squared. Not 8 to the 6th. They're being added. They're like terms. Add them up. Here we're approaching 2 from the right side, which is like 2.0001. So we're going to get 2 over 0. But is it a positive 0 or negative 0? It's going to be a positive 0 because this is a little more than that. So it's going to go to positive infinity. Okay? Be careful. If this was flipped around like this, it would be negative infinity because you'd be taking something a little more than 2 away from 2. So be careful. I'm looking for some indication that you are thinking about the 0 not really being 0, but being something tiny, and it could be something tiny positive or tiny negative, which makes a big difference in your answer. Here, if we plug in 3, we get 4 over 0. But is it positive or negative? Now, I think it makes it easier if you can factor this first, because this is going to be 3. Whatever. This is going to be 3 plus, which is something from the right of 3. So 3.0001, which makes this a negative tiny quantity. So this is going to negative infinity. So be careful. Okay, next one, you should be like, hey, that looks like a derivative, right? What's the function? 3x cubed. This is where the x usually goes. And what's the derivative of that? 9x squared. And then we're going to plug 2 into it. And we're going to get 36. Next one. Hey, that's a derivative. What's the function? Sine x. What's the derivative of sine x? Cosine x. All right, what's the derivative when you plug pi into it? Now, if there were x's here, you would just say cosine x, but we're going to plug pi into it, and I need you to simplify it. -1. If it's trig of some common angle, I don't want that as your final answer. Simplify. Here's a piecewise graph. So, I mean, what we could do is, the lazy way is to plug 4 into both pieces and see if they meet each other. Actually, both sides do approach 22, so this doesn't even need to be true. This, if it were continuous, it needs to be, but the limit as x approaches 4 from the left-hand side equals the limit as x approaches. This is a better way to show you work. Okay, and then you can show the limit as x approaches 4 from the right side. And it's the same thing. So that means that over the two-sided limit must equal 22 also. Similar idea here. Well, this is saying that f of x is continuous. So then what would have to be true? Well, the limit would have to, definition of continuity says that the limit approaches 0 of f of x, it needs to equal f of 0. Okay. So, well, what's the limit as x approaches 0 of sine x over 3x? Well, the trick we know is that this right here goes to 1, and I'm fine with that. So it's going to be 1/3, which means that f of 0 is equal 1/3, and f of 0 equals k, so k needs to equal 1/3. Okay. Next one's a good sandwich theorem one. This is not one that would be that one stuff. That's if it was going to 0. So now, I mean, I think if you, in reality, you're like, well, this is between -1 and 1, and this is going to infinity. Well, just any number between -1 and 1 divided by infinity is going to be 0. So my instinct is the answer is 0, but I want you to show me. So we're going to start with this, right? And we're going to multiply through by 1/4x. Now, if x is negative, we got to flip all these inequality signs. But in the end, it's not going to really matter which way they face. So now, as x goes to infinity, this goes to 0, and this goes to 0. So this has to be stuck in between them, and it's got to be 0. So this is what I want you to write. Since the limit as x goes to infinity of negative 1 over 4x equals the limit as x goes to infinity of positive 1 over 4x, both equal 0, then, now you got to have this also with this. So it starts with this, and then this is the next technical thing, and this, then the limit as x approaches infinity of sine of 3x over 4x equals 0. Okay. Problem 20, in behavior. Now, in behavior is both ends. I could also say just right end behavior or just left end behavior. In behavior includes both of these, but I might just might simplify it to one. So that means you got to show, yeah, I mean, it can be different for positive infinity and negative infinity. Now, it's definitely going to involve the dominant terms. If you go to positive infinity or negative infinity, these are the dominant terms. And so either way, now sometimes if you go negative infinity, different terms will become dominant and whatever. But for both of these, it's going to be negative 2 over 7x cubed. This is what the function will tend to go towards, kind of like an asymptote, but a curve instead of a line. So here's the dominant terms. Whether you plug negative infinity or positive infinity, these are the dominant terms. And so it's going to go to negative 2 over 3x both ways. So this is REBF and LEBF, dominant terms. But I'm just warning you, sometimes it can get tricky. Now be careful of the negatives and stuff. That matters right there. Okay? And all that's left now are problems without L'Hopital's rule. Now, also on the test, there will be a one question that is a sign regression problem. That's like one of those sign regression problems in the homework where I give you one sign regression problem, but maybe ask you 3 or 4 different questions about that one problem. And you'll be allowed to use a calculator on that, but not on any of these. So part A, identify the original indeterminate form and then find the limit. So on the test, I think I'll probably have 2 different places for your answers, part A and part B. Okay. I don't have that here on the pretest. Okay. Now, as we go to 0, we get 0 over 0. So that's the initial indeterminate form. Okay. And so we've been doing a lot of these. So L'Hopital's rule, we're not going to use other techniques, even if you want to. Got to do L'Hopital's on these. You need to write the limit every time. You got to show me the indeterminate form. So I'm just going to clean this up. It should be a 1, actually. And now if I plug 0 in here, I get 1/2. Okay. Let's see. This one, if I plug 0 in, square root of 1 is 1, minus 1 is 0, minus 0 over 2 is 0, is 0 over 0. That's the initial indeterminate form. And you got to show me 0 over 0 or infinity over infinity before you can do L'Hopital's. Sometimes you're going to get other indeterminate forms, which will maybe be the initial indeterminate form. So now if you plug 0 into this, you're going to get 0 over 0 again. Okay, I need to see that if we do L'Hopital's again. And we do L'Hopital's again. And you might be tempted to clean it up, which maybe that'll help, maybe not. Now I'm going to go and clean it up. So I'm not doing L'Hopital's rule. I'm just going to simplify this. I'm going to say, okay, well, this is going to be 1 over 8, 1 plus x to the 3/2, positive exponent. So it's going to be 1/8. Actually, I lost a negative. No good. Negative 1/8. Okay. Now ignore the numbering here. I'm just going to go ahead and do these right now, even though probably the next few are still the kind of classic indeterminate forms, but we'll do some of these now. So we plug 0 in here. Tangent is sine over cosine. And natural log graph looks like this. So if you go sine of 0 is 0 over cosine of 0 is 1. So that's going to be 0 times negative infinity. So this is the initial indeterminate form. Okay? Now, we can't do L'Hopital's rule with that yet. So we got to change this into a fraction. Now, I'm gonna take the easier way out. Well, I don't know. There's different ways that we do this, but I'll go ahead and make this a little hard. Now, what would be less messy, to put the natural log in the bottom or the tangent? I think the tangent, because if we put the tangent in the bottom, that's the same thing as 1 over cotangent. So we could do that, right? And then it's cosine of sine, and so it's going to be negative infinity over positive infinity. So I can do L'Hopital's rule now, and that's going to be 1 over x on the top. Derivative tangent secant squared. Cotangent is cosecant squared negative. Which I'm going to go ahead and clean this up and say, okay, well, that would be cosecant is 1 over sine squared. So it's going to be negative sine squared on the top over x. So we plug 0 into here, we get 0 over 0. Again, so we've got to do L'Hopital's rule again. And that's going to be negative 2 sine x to the first power times cosine x. You got to be careful. This is the same thing as sine x squared. So that's a chain rule thing. You got to do the outer derivative first, leave the inside the same, then the derivative of the inside. All over 1. If we do 0 now, we get 0. Right? Just get 0. Okay, this one, like I said, we're getting some of these weird ones right away just because of the way I did this. That's the initial indeterminate form, which is going to go in your answer column on your test. Now, in these ones, our trick is to bring in natural logs to help us. So we got to kind of tweak bring that in front, and then we're going to take the limit as x goes to infinity of natural log of f of x equals the limit as x goes to infinity of x times natural log of 1 minus 3 over x. And that's going to be infinity times 0. Right? Actually, I think approaching 1 from the left-hand side is going to be negative 0. So now we know we got to change this into a fraction then. But this is something you're going to show me that tells me, oh, okay, yeah, we got to change this into a fraction. Now, I'm going to leave the natural log on top because it's way messy, and making it into a fraction of the denominator would be horrible. Now, it's going to positive 0 over positive 0. So now we do L'Hopital's rule. So it's going to be 1 over what's inside times derivative of what's inside. Okay, so the x squareds are going to cancel. We could we clean it up just to make it easier to look at if you want. So there's going to be a negative 3 on top. I don't need to change it into I don't need to get rid of the complex fraction, but this is going to go to 0, so the answer is going to be negative 3. But that's not your answer yet, because remember, we have to re-exponentiate the answer. The limit as x goes to infinity of f of x equals the limit as x goes to infinity of e to the natural log of f of x, which is what we just found. So that's going to be e to the negative 3, which is going to be 1 over e cubed. Be kind of the nicest answer to write for that. So then a couple tough ones with some easy ones. So on to the last page. Okay. Okay, so here we're going from 0 from the left, which means this is going to be 0, but negative. And 0 from left here is going to be 0 negative squared. But it's 0 over 0 for all we need. That's your initial indeterminate form, which also allows you to do L'Hopital's rule right away. Got to keep that superscript negative. Cosine x over 2x. So if we plug 0 into here, we get 1 over 0, but it's going to be negative because we're approaching from the left, which is going to make it go to negative infinity. So if you don't deal with that negative 0, you're going to get the wrong answer. Negative infinity. This one, secant is 1 over cosine. Tangent is sine over cosine. So that's going to be cosine of pi over 2 is 0. So that's going to be infinity over infinity. So that's the initial indeterminate form, which will go in your answer column on your test. So we could go ahead and do L'Hopital's rule. We could leave it with that. Secant is secant tan. And tangent is secant squared. And then, so it's going to be sine over cosine over 1 over cosine. So we could go ahead and simplify that and take the limit as x goes to pi over 2 of sine x, which is 1. Okay. 25. Natural goes to infinity over infinity, initial indeterminate form. So we can go ahead and do L'Hopital's rule. It's going to be 1 over x over x to the negative 1/2. Now I'm going to simplify this now. So this is the same thing as 1 over x to the 1/2, and then we're going to multiply by the reciprocal. So it's going to end up being x to the 1/2 over x to the first, and we use rules of exponents and say, okay, well, that's 1 over x to the 1/2, which is square root of x, which gives you 0. Next one is going to infinity times sine of 0 is 0, initial indeterminate form. So we've got to try and change it to a fraction. What should we move to the bottom? Just the plain old x or the sine of 1 over x? The easy, simpler one should go to the bottom. Okay, so now it's going to be 0 over 0. And so now we do L'Hopital's rule. And that's going to be cosine of 1 over x times the derivative what's inside, negative 1 over x squared. That's going to be negative 1 over x squared. Those cancel each other out. So cosine of 0 is 1. Okay, this one's going to positive infinity, so it's going to be infinity over infinity. Initial indeterminate form. We can do L'Hopital's rule now. And it's going to be 1 over e to the x. It's going to be 0. Okay, next one, we're going over positive infinity minus positive infinity. So this is infinity minus infinity for your answer column. If it were infinity plus infinity, that's infinity. If it were negative infinity minus infinity, that'd be negative infinity. That's not indeterminate. This is indeterminate. So our strategy we've been talking about is that those must be coming from fractions. And if they're not fractions, try and think of them as fractions. These ones are. I'm going to combine them together into the same fraction, use least common denominator. And so now we're going to get 0 over 0. So now we can do L'Hopital's rule. Cosine x minus 1 over, I got to do product rule on the bottom, x cosine x plus sine x times 1. Now if I plug 0 into this, I get 1 minus 1 is 0 on the top, 0 on the bottom. So we're going to do it again. This is going to be negative sine x. This is going to be x times negative sine x plus cosine x times 1 plus cosine x. So if we plug 0 in here, we get 0 over 0, 1, 0 over 2. I'm looking for that. And the final answer is 0, but I'm hoping to see a 0 over 2. Okay. Now back to some more interesting ones. 0 to the 0, initial indeterminate form. So we're going to create a function, take the natural log of both sides, use a power rule, move in front, take the limit of this new natural log of the function. We need to be keeping this 0 plus coming, and I'm about to show you why. Because when you plug this in, that's going to be 0 times. Now, if you're approaching natural log of x, you can't just do x going to 0 because it doesn't exist on the left-hand side and it doesn't exist in general. There's a vertical asymptote. But on the right-hand side, it's going to negative infinity. So that's your next indeterminate form. I'm expecting to see that negative. This is positive. So then we got to put this in, make this into a fraction. So I'm going to do natural log of x over 1 over x, and that's going to be negative infinity over positive infinity. So I'm expecting to get a negative answer. And so then we can do L'Hopital's rule. I'm just going to do it over here because I'm running out of room. You'll have a lot more room tomorrow. A lot more room. 1 over x, negative 1 over x squared. And clean it up. So it's negative x. It's just negative x. So it's just going to 0. But you need to re-exponentiate. So the limit as x goes to 0 plus of the function, the original function, that's not what we just found. We found the natural log of the function. So we're going to use that and re-exponentiate it. So those would cancel, but it's going to be e to the 0. Final answer is 1. Don't forget to re-exponentiate those ones that we use that natural log trick on, okay? Okay, next one. This is going to 1 to the infinity. So we're going to use a similar trick last time. So I don't know. I mean, these are a bit of work, but kind of go through the motions. I mean, you know what you hopefully you know what's going to happen. Now, when we go to infinity, that's going to be infinity times cosine of 0 is 1. Natural log of 1 is going towards 0. So that's your next one. So then we got to turn that into a fraction. Leave the natural log on top. Unless you're like, this is too easy. I want to make it really hard. So that's going to be 0 over 0. So now we can do L'Hopital's rule. Ooh, this one's going to be gross. 1 over what's inside times derivative what's inside times derivative what's inside that. Ugh. Okay, can we clean that up? So the negative 2's cancel each other out. We'll get a negative x sine 2 over x over cosine 2 over x, which gives you sine of 0 is 0, 0, 0 over 1. Thankfully, that's done. We've got to re-exponentiate it. So the limit as x goes to infinity of f of x equals the limit as x goes to infinity of e to the natural log of f of x, which equals e to the 0, which equals 1. Okay? Okay, getting close. This is going to be 0 over 0. All right. Nice. Okay. So it's going to be cosine 5x squared times 10x over 6x. The x's cancel. Plug 0 and that's going to be 1. So we're going to get 5/3. That was refreshingly easy. Okay, this one, a, b are constants, they're numbers. So if you plug infinity in, we're getting 1 to the infinity is our initial indeterminate form. So we're going to do a little trick. Take the natural log of both sides. So we use power rule, bring it out in front. Take limit. It's going to be infinity times 0. So we need to change it to a fraction. Now my advice here, and hopefully you follow it, is to leave the b in the top. So b times the derivative of that is going to be 1 plus a over x and now times negative a over x squared all over, and then just, oh shoot, I'm getting ahead of myself. Just leave the b in the top, and x will be in the bottom like that. Now if we plug infinity into this, we get 0 over 0. So now we can do L'Hopital's rule, which I was starting to do ahead of time. Now, just leave the b. The b is just a number, okay? So it's going to be 1 over 1 plus a over x times derivative. That's going to be negative a over x squared. And then the b could just be right up there where the 1 is. And the bottom's going to be negative 1 over x squared. So the negatives are going to cancel. The x squareds are going to cancel. We could clean this up. It would be ab over 1 plus a over x as this goes to infinity. That's going to be 0. So the answer is going to be ab. But we still have to re-exponentiate it. So it's going to end up being, I'm just going to cut this out. I'm going to cut out the normal work that you should show just because I'm just running out of room. On your test, you'll for sure have enough room. I can show it down here if you want, but that's it. Okay, let's see this one. Now this is interesting. This involves an integral. So, I mean, I guess we could integrate it, right? It's the antiderivative of sine. Negative cosine. Okay. And then, so that'd be negative 4 cosine 4 minus plus plus cosine x squared over x squared minus 4. So we're going to take the limit of that. So it's going to be negative cosine 4 plus cosine 4 is 0 over 0. So I'd say that's our initial indeterminate form. I mean, if you plugged in up here, it'd be 0 over 0 also. So, I mean, you could do it right away and just say it's 0 over 0, and that's the initial indeterminate form. Now, before we start doing, that's interesting. I'll come back to that in a second. Because if we can do L'Hopital's rule, then we do fundamental thermocalculus part 2. But I'm gonna do it like this, and then I'll do it the other way. So take the derivative of the top. It's gonna be negative sine x squared times 2x over 2x on the bottom. Let's cancel out. I'm going to get negative sine 4. Negative sine 4. Now, if instead up here, if you went down here and you say, well, okay, let's take the derivative of the top and bottom. The derivative of the top, fundamental theorem of calculus, the derivative is going to cancel out the integral, and then you got to plug in the top limit, and then you got to plug in the bottom limit. But you got to multiply by the derivative of the thing you plugged in, which would be 0 for this guy, and this guy is going to be 2x. Over the bottom, the derivative is 2x. So this goes away. These 2x's cancel, and we get negative sine of 4. You got to be careful with that. I kind of like that way. So, all right, some good practice, but also remember there will be a sign regression problem also.